Okay, welcome to end of chapter 18, problems. These should be pretty efficiently done. I'm sure that after completing the lecture for this chapter and having gone through the previous weeks of the semester, this is a welcomed gift. So knock it out of the park, so to speak. All right, so in number one, they give you portfolios, P, Q, R, S, and they give you market portfolio information in the textbook. They hand you the returns, right? They say during the period under consideration. So these are the average returns during the time period. Then they hand you the beta coefficients, which is the measure of systematic risk in the table. And then they give you sigma, which is a measure of total risk in the table. A, compute the Sharpe measure, right, for all portfolios. B, compute the Traynor measure for all portfolios. C, rank the portfolios using each of these two measures and explain the differences in the rankings if there are some, right? So that's what we're going to do in number one. Right? All right, so you can see right here on the screen, we have, let me find my pencil here, right? We have the Sharpe ratios computed for all of the portfolios, P, Q, R, S, and then M, the market. You could write, S sub M here, right? So you take the average return minus the average treasury bill rate during the time period. In the textbook, right above the table, they hand you RFR is 0.07. Right? So we plug and chug, and we get the Sharpe ratios for all 5 portfolios, including the market portfolio. Now remember in lecture, these are the Sharpe ratios. Since the Sharpe measure uses sigma in the denominator, total risk, these will plot on the CML graph. Right? Remember the x-axis on the CML is the total risk measure sigma. Also remember that by definition, the market's Sharpe ratio plots directly on the CML. So that number is on the line. All right, does anybody see a clear first place? We'll get to the ranking solutions here in a moment, but we can do this like we did in lecture. We want our Sharpe ratio to be as high as possible. This is the highest. So S is first place, according to the Sharpe technique, followed by P, followed by the market. That's third. Then we've got fourth and fifth. Fourth and fifth both underperformed the market on a risk-adjusted basis. Fund manager S and P both outperformed the market on a risk-adjusted basis. All right, then B, they want the Traynor. Do the numerators change in this problem for the Traynor ratio? The answer is no. The only thing that changes is our risk measure for Traynor in the denominator is now beta, right, which measures only systematic risk. So we plug and chug, and we get the Traynor measures for all 5 portfolios. Right? Here they are. Again, the higher the better. The market's Traynor would plot directly on the SML. Now it's the security market line because we're using beta as our relevant risk measure, right? And the assumption is if you're using the Traynor approach, your assumption is that these portfolios must be completely diversified because you're only allowing systematic risk to be present through beta, right? All right, which one is the highest number up here? This one looks to be the highest. So fund manager S is the winner according to the Traynor approach. They were also the winner using the Sharpe, right? I guess we can say they're a winner. Number 2, second place. I'm just eyeballing this. Portfolio Q looks to be second place. Up there, Portfolio Q was 4th place and underperformed. Here they outperformed the market on a risk-adjusted basis, so that's second place. We're doing relative rankings, not absolute. Followed by third place, Portfolio P. Then 4th place would be the market, and then last and 5th place would be R. And R was last place in both the Sharpe and the Traynor technique. So we could probably conclude that R is a loser And we'll call portfolio our loser, not the human being running the portfolio. We don't want to go to HR. All right. They ask you to rank them. We already ranked them. S was the clear winner under both of the techniques. Q was a surprise. It was underperforming the market on a risk-adjusted basis and almost next to last. Here it was next to first, right? R was fifth in both cases. Right? It says it is apparent from the rankings that portfolio Q was poorly diversified because Trainer ranked at number 2 and Sharpe ranked at number 4. Otherwise, the rankings are similar, right? So that means there must have been some unsystematic risk present in portfolio Q. It was not diversified. It was poorly diversified. All right, that's it for number 1. Okay, this is the solution for problem 2. Problem 2 in the textbook, they give you information about one risky portfolio. They call it X. And then they want you to compare that to the market information. What do they give us here for the market? The Standard & Poor's 500 index. That's what they use as the market portfolio. They hand us in the table in the textbook the R bars, average annual rate of return. The first column is R bar. The second column is standard deviation of return. That's sigma, measures total risk. And then the last column is beta, right? That measures only systematic risk. In part A, they want you to briefly explain whether portfolio X underperformed, equaled, or outperformed the S&P 500 on a risk-adjusted basis using both Trainer and Sharpe. So we will do them in that order. Here is the Trainer measure formula. Looks slightly different. In lecture, it was R bar minus R bar sub I minus R bar RFR. Right, same idea. Take the return to the risky portfolio X minus the average treasury bill rate during that time period, 6, divide by beta of fund X in this example. You get 6.7%. Here's the Trainer on the market. You get 6%. Remember that this would plot directly on the SML because it's Trainer. That is above. So we can conclude that the portfolio X outperformed the market on a risk-adjusted basis if we use the Trainer measure. Here, all of that is explained to you. Then they want you to do it the Sharpe method or Sharpe technique. Okay, so the information for the Sharpe is right here. They give you an explanation. To get the Sharpe ratio for fund manager X, you take the return to fund manager X minus the risk-free rate divided by sigma for fund manager X. Here it is. 10 minus 6 over 18 gives you 0.222. 12 minus 6 over 13 gives you 0.462. Right? The Sharpe ratio for the market portfolio plots directly on the CML. That number is below the CML number. So we say that fund manager X, if we use the Sharpe technique, underperformed the market on a risk-adjusted basis. And they're using these numbers here. By the way, you can get rid of that. That's not there, and that's not there. The units cancel, right? 0.222, 0.462. Okay, part B of problem 2 says, based on the performance of portfolio X relative to the S&P 500 in A, the part we just concluded, explain the reason for the conflicting results using either the Trainer versus the Sharpe. And remember, the Trainer uses beta as the risk measure, so it assumes the portfolio is completely diversified and that the only type of risk present is systematic risk, which is measured by beta. If you do the Sharpe technique, it allows for there to be some unsystematic risk present, which means the portfolio would not be perfectly diversified. They explain that right down here for you. The Trainer measure implicitly assumes the portfolio being measured is fully diversified. The Sharpe measure is similar. However, for perfectly diversified portfolios, the Trainer and the Sharpe measures would give consistent results because the only type of risk that would be present would be systematic, and beta would then equal sigma at that point. Right? Now, I won't read this to you. When you're studying, you can read this and feel free to send me an email and ask me anything about that, right? Portfolio X outperformed the market if measured by the Trainer measure, but did not perform as well as the market using the Sharpe measure. The reason is Portfolio X has a large amount of unsystematic risk present, right? We didn't know that, but that's what it means when you get conflicting results. The Sharpe technique said the portfolio underperformed the market on a risk-adjusted basis. If the Trainer says that it outperformed, well, that means there must be some unsystematic risk present in Portfolio X, right? I won't ask you anything about this R-squared business. Okay, problem 3, right? There's parts A, B, and C. If you have the textbook in front of you or you just looked at it, you can see they hand you a regression equation at the top. It says we have been assigned the task of comparing the investment performance of 5 different pension fund managers, right? So the portfolio's names, you can see in the table, are A, B, C, then D, E, F, then G, H, I, then pension fund manager JKL, and then lastly MNO, right? They hand you the regression data information, they hand you alphas, they hand you betas, and they hand you R-squareds, right? And then in the final 2 columns of the table, they hand you what they call mean and sigma. So that mean is R bar, right? Actually, I lied. That mean, this table is confusing. Let me actually show you right here real quick. All right, this is the textbook problem. Where it says mean right here, they're talking about the mean of this whole damn thing, right? Usually it's not presented that way. That's why I was startled. Startled is a strong word. This 1.022, this is the average of the entire numerator in the Sharpe and Trainer. Remember, the Sharpe and Trainer ratio both had R bar minus RF R bar. So this would be the entire numerator. It's done for you, the minus RFR. And then sigma, that's pretty straightforward, right? All right, so we're going to go through these. A, which fund had the highest degree of diversification over the sample period? How is diversification measured? B, rank these funds using the Sharpe, Trainer, and Jensen measures. And then talk about C, talk about the alphas. Which funds have significantly outperformed and underperformed the market, right? Don't worry, we're not diving too deep in statistics. All right, so A, which fund had the highest level of diversification? They tell you to look at the R-squared. I won't ask you the details, I'm not your stats professor, but the highest R-squared means the most diversification in this example, and that was portfolio MNO had an R-squared of 94.8%. Great, we're going to move along. All right, now they wanted us to do the Sharpe ratio, the Trainer ratio, and then do the Jensen's alpha approach, right? And then in the last part, talk about significance. All right, so the Sharpe measure, right? There's that number that I mentioned in that next to last column in the table. That's R bar on this fund minus the average risk-free rate. It's done for you. So that's the entire numerator for the Sharpe ratio, right? We divide by sigma because Sharpe uses total risk, standard deviation. There it is. You do that for all 5 funds. We always want our Sharpe ratio to be as high as possible. Which one is the highest? This one. It gets first place according to the Sharpe technique. Fund manager GHI. What's the next one? This one, that's second, relatively speaking. The next one, that should be third, fourth, fifth. Okay. Perfect. Let's see. Trainer, same thing. The numerator is identical to the Sharpe ratio, so we just plug them over here. Now we're dividing by the relevant risk measure, which is beta, only systematic risk. So the betas get plucked directly off the table in the book. We rank them. This is the highest trainer measure, followed by that one, followed by MNO, then ABC, then DEF, right? The funds. Okay, so those change slightly. These are identical, so is first place. JKL and MNO just happen to swap places for second and third relative rankings. All right, now over here where it says the Jensen's Alpha, right? They rank these, they pluck them off the table. Remember, we want our alpha to be highly positive, actually. So they put this one as 1, right? This one's ranked second, third, fourth, and fifth. But those alphas plucked off of that table are just estimates, and we have no idea whether they are what are called noisy estimates in statistics, meaning we haven't tested them for statistical significance, which is what the part C of this problem asks us to do, right? And so I don't think these are valid rankings, right? I had this discussion with my investments class about a year ago, and then I went to AI, and this is what Google AI stated. When ranking funds using Jensen's Alpha, and this, by the way, is Jensen's Alpha, plucked right out of the book, right? When ranking the funds, it is crucial to consider statistical significance, meaning you should only rank funds based on alpha values that are statistically significant. So just by looking at these numbers plucked out of the book, out of the regression, right, somebody came up with them, doesn't mean we can rank them like this. So I would say that's kind of shoddy, right? A non-significant alpha could be attributed to random chance and not true skill by the fund manager. Essentially, a positive alpha with a low statistical significance wouldn't provide reliable information for ranking purposes. So I think this last column is nonsense. Right? All right. Here is how we can actually talk about the alphas meaningful. So I wrote here, and you might be looking at that and going, "Oh crap, that's back." Those are dark times in most undergrad students' lives. The test statistic, the t-stat, is equal to alpha hat. This alpha hat is in the textbook, right? In fact, this alpha hat is right there for fund manager ABC, right? This alpha hat belongs to fund manager MNO. We're subtracting 0 because the hypothesized value is 0, and we're dividing by the standard error of the alpha. In the textbook, in the problem, right, you have the alphas and the standard errors handed to you, right? The standard errors are directly under the alpha hats, right? So in the table, the number in parentheses under the alpha is what I wrote here, standard error of alpha, right? So that's where we're getting these numbers from. So if you do that, if you take 0.192 and divide by its standard error in the book, 0.11, you'll get 1.7455. This is the test statistic that we would then compare to the number 2, right? At an absolute value, number 2, right? 1.7455 is not greater than 2. We would say that fund manager ABC's alpha, even though it's positive, it is not significant, right? I'll do another one. Here is the test stat for fund manager DEF. Well, first of all, it's a negative. That's not bragging rights in the investment community. Negative alphas mean you underperformed. But let's check the significance of it. We would take, right? Actually, no, this is the test stat ready to go. Compare this number to -2, right? This number is not less than -2. Let me give you this. You've seen this before. You probably don't want to ever see it again. Let's call that +2 and -2. This negative number is somewhere in here. So we would call that not significant. So it is negative, but it's not significantly negative, right? Just like this 1.74, it was 1. It's in this region. It's not significant though, right? All right, how about this one, 2.43? Yeah, that's over here. that's in the shaded region, that is significant. And fund manager GHI would be first place. They have a positive alpha and it is significant. This one is positive, but it's not significant. It would be somewhere in here. This is positive and it is significant. So we would probably call this first place, second place, third place, fourth place, last place, if we were ranking them. Here's the last problem we will look at in the chapter, number 5. It says we have information from the past decade for two managers, manager X and Y. Right? These are annual returns. For each manager, calculate the average annual return. So they want R bar sub X and R bar sub Y. Calculate the standard deviation of returns. On this graded assignment, I won't ask you to do that because on a previous one in the semester, I've already asked you to compute standard deviation for an individual asset, right? So I'll hand you those. That's sigma, that's total risk. And then semi-deviation of returns. Remember, that was downside risk from the Sortino measure. B, assuming the average annual risk-free rate during the 10-year period was 1.5, so that's RFR, bar. Calculate the Sharpe ratio for each portfolio. Based on this, which manager appears to perform the best? C, calculate the Sortino measure. Which manager performs the best? And when would you expect Sharpe and Sortino measures to provide the same performance ranking or different? Right. So this is the Sortino example from the lecture, right? Similar to. Right. There are the solutions files provided, but this one was done incorrectly in a previous version of the textbook, so I've just written it out by hand. So you do have the solutions file that comes from the chapter that you've just been looking at over and over again. Here's my handwritten solution, right? When you add those 10 numbers up for portfolio X in the book and you divide by 10, you should get R bar X is 4.5%. Do the same thing for fund manager Y. Add those 10 numbers up, divide by 10, you should get the average return of fund Y is 4.5%. So they had the same average annual rate of return. When you're handed, I just told you I would hand you these. That's total risk of fund manager X, total risk of fund manager Y, right? You get these, right? 6.9, 6.633. All right. I computed semi-deviation first. Let me actually, hold on one second. Let me come back here. Yep. We'll just do it in the order that I wrote it out. We'll all end up at the same place and the same conclusions if we do our math correctly. So here's the semi-deviation, the downside risk. This was the formula we saw in the slides. Only include returns for fund X that are below the average return for fund X. Right? So if you have the book right in front of you, you will see that it's a loss of 1.5% gets included, a loss of 1.5% gets included. Same thing, a loss of 1%, and then a return of 0% in one of those years. So there were 1, 2, 3, 4, 5 of those 10 years of data that get included in computing downside risk because we only include returns less than the average. What was the average return for fund manager X? 4.5. That's why we only included the returns below that. We carry out the math, and you should get 5.63. So 5.63 is the downside risk for fund manager X. You do the exact same thing for fund manager Y, only include the returns to that portfolio that are below its average return of 4.5. A loss of 6.5% is included, so is a loss of 3.5, a loss of 1.5, a gain of 3.5%. Those are all below the average return of 4.5%. Divide by 4 here because there are only 4 of the 10 years for fund Y that get included in the downside risk computation. 7.45 is the DR measure for fund manager Y. Okay, part B asks you to do the Sharpe ratio, right, approach. So here's the Sharpe ratio for fund X versus Y. That was the average return minus the return to the treasury bill during the same time period divided by sigma, 0.435. Do the same thing for fund manager Y, 0.452. Remember in lecture, we always want our Sharpe ratios to be as high as possible because it is return divided by risk. We want that to be high. So if we use the Sharpe ratio, fund manager Y is the winner. If, however, we do the Sortino measure, same thing, right? Average return minus the average T-bill return divided by, but now this is the DR for fund manager X. This is the DR for fund manager Y. We want this number to be as high as possible, and now fund manager X is the winner. This is a repeat of what you just saw in my beautiful handwriting, right? That's just all a repeat of what you just saw. D says, why are they different, right? Why do they swap here? Under the Sharpe ratio, Y was the winner. Under the Sortino measure, which only includes returns below the average, it reversed, and fund manager X is the winner. Here it says the Sharpe and Sortino measures should provide the same performance ranking when the return distributions are symmetrical for the funds, right? Asymmetric distributions, such as when one manager is hedging risk exposure or using portfolio insurance strategy. Remember, we talked about that in the last chapter, protective put, right? The performance rankings should differ. I won't ask you too much about that, asymmetric distributions.